Next speaker is Lizzie Pratt.
All right, thank you. There's a slide. What? You can use the little. Oh, I can use the clicker to change the slides. Wonderful, thank you. Yeah, thank you, Thomas. Thank you, Lauren and Mateo for organizing. If you don't want to take notes or anything, the slides are on here, and please interrupt early and often. This is going to be based on some joint work with Bernd Sturmfels. The title is the Chow-Lam form. So it is named after two mathematicians, one in the 1930s and more recently. But first, I think I'm going to transport us back into the 1930s and just talk about the Chow form a little bit.
Can you speak a little louder?
Okay.
It's hard to hear here, so.
Okay. I will try to speak louder. Thank you. Okay, so the setup is that you have a projective variety of dimension d. You want to encode it by a single equation in zero coordinates. So you're going to associate to it a locus of linear spaces of codimension d plus 1, which actually meet the variety. And you're going to call this the Chow locus. So here, for example, is a curve in P3, and I'm looking at lines which meet it. So the red line is in the Chow locus, and the purple line is not because it doesn't meet the curve. It turns out that this is a codimension 1 condition on this Grassmannian. And so it has a single defining equation in Fluker coordinates, which is called the Chow form. And you notice there's some sort of off by ones here with the n minus 1 and the n, and that's because the Grassmannian, I guess here in example 2, 4 parameterizes lines in P3. It's given by like the span of 2 points. So if there's ever off by ones, just assume it's that and not error. Right, anyway. So when I say that the Chow form like encodes the projective variety, I mean like historically, these were used because of the property that you could actually completely recover the variety if I give you Chow form. So what are examples of these? One example is if I give you a hypersurface, and I ask for points which lie on the hypersurface. Just get back the defining equation of the hypersurface as my Chow form. Another example is if you take like a linear space and you ask for like linear spaces intersecting this linear space in some way, you'll also get like a Schubert variety, and it's a Schubert variety of codimension 1. So it's and I'm going to be using I'm going to be writing down some explicit equations during this talk, and I'm going to be using a couple different coordinate systems. One coming from representing my points in the Grassmannian as kernels of matrices, and one as row spans. I think probably the second one is a little bit more familiar. But just so that's clear, there are going to be some P's and some Q's floating around. Q means kernel, and P means Q stands for kernel, and P stands for span. Or no, sorry, the other way around. Q stands for row span, P stands for kernel. Right, so just to quickly flash an example for people who are coming at this from the algebraic geometry perspective, the Chow forms of curves are very interesting, well studied, and there's certain resultants. And there's been a lot of work on this by Eisenbud and Schreier. It's really cool, and you can sort of explicitly say what they are. Right, okay, so why were we interested in the Chow form? How did we come about it? We came to it from the point of view of projection. So one very nice property that the Chow form enjoys is that it behaves well under projection. Namely, if you take the Chow form of the image, and a linear space will intersect the Chow form of the image, if and only if the fiber, the linear space will intersect the image if and only if the fiber intersects the original variety. Sort of like see in this picture. And so that's very nice, because if we want to compute the Chow form of the image, what we can do is take the Chow form of the original variety, and we can sort of fix Z and express the Fluker coordinates of this fiber in terms of the Fluker coordinates of L and the matrix entries of C. And then whenever we fix Z, we'll just get for free the Chow form of the image. if you remember from before, if we project like low enough to the point where the image is a hypersurface, the Chow form of the image is just exactly the equation of the image. So, you know, eventually we can get down to like actually computing equations. But this leaves us with a question, which is namely, how do we actually like write down the Fluker coordinates of the fiber? So it turns out that physicists knew the answer to this question for much longer than we did. It turns out that these coordinates are exactly twistor coordinates, which we've seen sort of in the previous talks. Here we can recall the definition, which is that the ith twistor coordinate is the determinant of take z, take the columns index by I, stick on an L, and compute. So here's some examples. Just to make things like really, really concrete. We could take our twisted cubic equation over here, and we could like take a 3x4 matrix Z, so like project down to some plane, and express the coordinates here in terms of the Z's and the L's. And then if we plug in a particular Z, we'll actually just like get the equation of the image in terms of the like indeterminates on I should say P2 and the matrix entries.
Just a historical question. First place I've seen twistor coordinates is the paper of Nima, Q. Thomas, and Yara. Is that the accurate first place where they appeared, or did they appear implicitly in some other previous?
I thought that paper Nima refers to some like earlier paper, but I don't know. But also, I'm not sure with like twistor momentum space. And like, I think maybe this is a better question for the physicists in the audience.
I mean, before the Amplituhedra, there was no twistor coordinates.
There was like
there was no Y.
space, right?
Yeah, but that's slightly different.
Okay.
I mean, yeah, if you project the Amplituhedra into momentum twistors, then you get twistors, but that's after the projection.
Okay.
Well, I mean, there was, then there was.
I mean, but that's so the static reason by default is
But the actual twistor coordinates are like coordinates on the amplitude, so.
well,
Well,
yeah.
anyway, okay, maybe we should.
Yeah, but anyway, I really want to highlight that I had not seen this interpretation before of like the twistor coordinates as the coordinates of the fiber. And it's very like sort of satisfying from a geometric perspective. All right, so yeah, just to say also again, like the connection with projection, like this original Chow form really computes like universal projections, like you just express it in terms of Z. Okay, now we're sort of entering the realm of things that have appeared before in this conference. We want to generalize this Chow form to the Grassmannian context in such a way that it still has many of the properties that it used to have. For example, plays well with projections. And this whole sort of like project was inspired by reading these notes of Thomas, which I talked about projections of positroid varieties along with like 20 other things, and they're very nice. But yeah, so this is a particular kind of linear map between the Grassmannians, which is that we saw before in this conference, take a matrix representative and multiply it by Z, or if you like, it's like a linear map given by like k exterior power of Z, how we like to think about it. Right, so let me give you the definition, the new definition. We're going to fix a variety, and we're going to ask for it to have a particular dimension, one dimension lower than some Grassmannian, the Grassmannian, or K comma R. And we're going to define the Chow-Lam locus to be spaces, subspaces of dimension K plus N minus R, or which contain a subspace Q, where Q is a point in the original variety. So here I have kind of a different way of writing this, just to make it sort of more clearly connected to the Chow form and more clearly connected to some other things that we'll see later. But this is what we should really be thinking for our examples. And And unlike the Chow-Lam, unlike the Chow locus, the Chow-Lam locus will not always have codimension 1, but it usually has codimension 1. There's like it's the coefficient of a certain cohomology class, and the expansion of B, or in the cohomology expansion of B is non-zero, then it's not codimension. So it's like usually codimension 1, and when it is, it's defining an equation. It's called the Chow-Lam. So this is a kind of like big definition to wrap your head around, but you can sort of think of it as like, instead of like P intersects the variety, you're taking some sort of like Schubert variety with respect to P. And you're asking for that intersection to be non-empty. Okay, let's see sort of one example of these things. So we're going to start with a curve in the Grassmannian, and then we're going to take a surface given by take the union of all the lines. The line is the point on the curve. So you're going to go along the curve and just take the union of all of the lines. And we're going to interpret its Chow-Lam locus geometrically. So if we plug everything in, then we end up with the Chow-Lam locus being a surface in GR34, also known as a dual projected 3-space. And what is it? It is planes in P3 which contain a line for B. So it is planes in P3 which contain a line on this surface. Turns out with a little work, you can show that this is actually the projective dual of the surface. So the variety of the tangent planes S. And the way you argue this is you say, okay, well, if it's tangent, it contains a line. So one is in the other, and then you use a fact about the loci, which is their irreducible varieties. So there's sort of a nice algebraic geometry interpretation of this kind of things. But we're here at a physics math conference, so we care maybe about particular subvarieties of the Grassmannian, namely, skipping ahead, namely subvarieties that appear in the boundary of the positive Grassmannian or positroid varieties. So it seems that that's actually one example further. So first I'm just going to say the thing that has maybe been implicit throughout my talk, which is the projection interpretation still works. That you can still take your Chow-Lam form, you replace all your Blukers by twistors, and you just get the equation. But let's see how this plays out in some positroid variety examples. So if you don't know what a positroid variety is, I've just sort of defined it up here. It is given parametrically, or I've defined this one. It is given parametrically by 2x9 matrices, where the first 3 columns are parallel. The next 2 are parallel, next 2 are parallel, next 2 are parallel. Or like the first 3 are multiples of each other, and the next 2, and the next 2, and the next 2. This ends up being dimension 9. And it'll consist of row spans of matrices with basically the condition that I just said. And if you plug in all the numbers and run the machinery, you end up with the Chow-Lam locus being in GR49. So please bear with me, because this is the one example that I will do sort of in detail so that you can see how this works. But what is the Chow-Lam locus? Okay, it's going to be 4x9 matrices that contain, or parametrically given by 4x9 matrices that contain a 2x9 subspace in that row span, where that is an element of the variety. And you can say this, you can say like, okay, the 2 rows here must be some linear combination of like the 4 rows of X. That's where it gets some like T matrix, which expresses that linear combination. Okay. Now I go back here to my formula and I just plug in the tx everywhere. And I get another formula, like x is in the Chow-Lam locus if and only if there exists some t with these 4 equations. Okay, now we're going to do a very fun trick, which is we're going to interpret these equations geometrically. T is a 2x4 matrix. So we learned before that 2x4 matrices give lines in P3. This x1, 2, 3 is a 4x3 matrix. So it's a plane in P3. There's a line in P3, a line in P3, and a line in P3. And geometrically, what these rank conditions are saying is that the line in P3 given by AT is contained in the plane x1, 2, 3 and intersects with lines. Let me pause for a second and say we have rephrased the problem and not solved the problem, because the core difficulty when you're doing like projection computations is it's like an elimination problem. Like you have a point and you're asking, is it in the image? Does there exist some point that maps to it? Here we still have a statement of the form, does there exist some t with this property? So we have not eliminated the elimination yet. We have just translated this into a Schubert problem, but in a very nice way where you can kind of makes it easier to see what the elimination will be. So for which x does there exist a line in P3 contained in this plane and intersecting the other lines? Well, it's exactly when the intersection points of the 3 lines with the plane are collinear. And there's the magic, which is that I have like taken this, there exists condition and transformed it into a condition purely on x, like without t. So if you go through the motions, you can write this down in terms of the coordinates, the Pluker coordinates on x, and you get this nice determinantal expression. Yeah, and I think this is like really nice because when you look at these sort of like positroid examples, you always get these sort of like nice Schubert problems. And all the examples that I've computed are determinantal also, but only up to a pretty low degree. So I wouldn't take that as too indicative, but you do get some really nice Schubert problems out of it. Just to sort of flash another example on screen, it's another positroid variety, sort of where the first 2 columns are dependent and so on and so forth with the pairs. And you end up reducing it to the Schubert condition that these 5 lines have a common transversal. And when you write down the Chow-Lam form, you also end up getting sort of determinantal expression. So this is like a positroid cell, which such that the map down to the amplituhedron is like degree 5 algebraically. Great, okay. So I want to give one more definition. This definition is going towards something that we've seen a lot in this conference, namely the fabled 4-mass box. So we'll get to it on the next slide, but we sort of have to look at this definition first. There are a lot of sort of higher Chow forms, which capture non-transverse intersections. So like, you could ask, when does a line intersect my curve? You could also ask, when does like a plane, when is a plane tangent to my curve in P3? Like when does this sort of non-generic intersection behavior happen? And the next one up is exactly the Hurwitz locus. So the example with the line and the plane. I just have the sort of definition here, and it looks like the definition earlier. The interesting thing about this is that just as the Chow-Lam form computed equations of projections, the Hurwitz-Lam form also contains, or can also compute equations of branch loci. So it sort of contains all the information about any branch loci for any linear projection. So now the promised four-mass box. There is, by the way, I'm gonna defer to physicists to explain exactly why it's called the four-mass box. My understanding is that there's just like a diagram that's like a box, and it has like four external legs. So like I was originally kind of sad because I wanted to stick like a Q90 at the end here and call it a five-mass box, but apparently this was physically nonsense. But anyway, so this is the four-mass box. And its Hurwitz-Lam form will live in GR48, and it'll consist of matrices where we have the same system of equations as before, and we want it to have like fewer solutions than expected. So in other words, we want matrices such that there only exists like one T. If you've ever taken a course in Schubert calculus, like the first thing they ask you when you come in the door is like, if I give you 4 lines in P3, how many common transversals do they have? Like how many lines are there that meet all the 4 lines? As like the first thing you learn in Schubert calculus is that it's like 2. But here I'm asking for the matrices where it's 1. Yeah, I don't know, you also get a nice determinantal expression for this. Actually, we computed it through much difficulty, and it was only after talking to Mark that I learned of this nice determinantal expression. But yeah, so I think this is really neat. This sort of like types of problems that show up in the computations of Chow-Lam forms of positroid varieties in particular have this very nice structure that I don't fully understand why it exists. I think, you know, this is an amplituhedron conference, so I give an amplituhedron examples, but there are also lots of other questions that you can sort of like ask about other interesting subvarieties of the Grassmannian. And yeah, I don't know, I would love to talk more about it, and thank you so much for listening.
Michael, any questions?
You mentioned briefly, how do you compute the degree of the polynomial in Kluger's cutting out the image of your positroid variety into Amplituhedra?
Yeah, so the degree will be the homology.
It doesn't have to be super explicit.
Okay.
But more conceptual, yeah.
Yeah. So what you do is you compute the cohomology class, and you compute the coefficient of a certain Schur class, like a certain Schubert class, and that'll give you the degree of the Chow. The degree of the Chow form is just the degree of the original. Yeah. There's a follow-up question of, okay, how do you compute the cohomology class? And this in general, I think, is like not like, that sort of depends on the context and the positroid variety context in particular. Yes. Yeah.
Exactly.
So actually, the determinantal form, there are some, I'm not sure it's related, more precisely to what you're talking about, but there is this problem of finding in determinantal form the expression of highest frequency.
Oh, I don't know about this. That's interesting. Yeah, in this case, it's like kind of nice because you can sort of like, I mean, once you look at the determinant, you can kind of see the linear spaces given by the vanishing of the rows are sort of like obviously contained in your
Is there something like a ready master question involved in this calculation? There is this notion of determinants of complexes.
Some
I say,
determinants of what?
so there is this notion of determinants of complexes, and that's what emerges in this higher situations. I wonder if that's where this calculation comes from. So this multivariate complex that you can convert sometime.
Maybe this is exactly what happens in the curve case, is they write down a complex and then the like sort of final map in the complex. But like this is the Algebras stuff, final map in the complex. It's like some matrix and take the determinant. So I do wonder if there's a complex lurking in the background. It could be. I haven't really studied it from that point. The remark I wanted to make here is that when one of these like rows vanishes, it's like when the line 1, 2 meets the other 3. Is that? Yeah. Yes. Well, maybe it's easier to see with this one when you're asking for the 5 to have a common transversal. Like when this row vanishes, it's because the line 1, 2 meets the other 4, in which case the 5 do have a common transversal, namely the line 1, 2. So you can sort of like interpret the linear spaces coming from the determinantal expression in terms of the geometry of the sheet. That's maybe not an answer, but just sort of related remark.
To connect further to the themes of this conference, in case you have positroid varieties which are boundaries of positroid varieties that are tiles, that give tiles, then the Chow-Lam form is conjectured to be a cluster variable in the Grassmannian M, N, where M is the Amplituhedra that connects to the older story of cluster adjacency. And I was wondering whether there is any way to understand what class of polynomials you get out of these Chow-Lam forms in relation to cluster algebras and positivity.
Yeah, I think that's let me actually make sure I understand. So you have any positroid variety, which is a facet of a tile?
Yeah.
Okay. And
I mean, some of them would give 0 because they're mapping in a lower codimension, but the one mapping in codimension 1, they're correspond to facets in the image if you have tiles. And then those are cut out by polynomials that are cluster variables. That's conjecture in general, but proved in all the examples that we see in this conference. And it was true, and it was for with VCW, etc. So is there any understanding why that should be the case from the perspective of the Chow-Lam form?
I think the other question you asked, which is what sorts of polynomials are these, is maybe like a more tractable question for me to answer. I don't really know, but like you can see there's some kind of like structure here.
There's a clear connection to cluster algebras for positroid varieties that are giving tiles, and maybe even more, but at least for those. So there should be something you might be able to see from the Chow-Lam form.
I think that'd be very interesting. I think if you have any way to connect the cluster algebra to sort of like the geometry of the problem, I feel like these are sort of like getting from here to here is kind of hard to compute. So if you could get a way to get from the cluster algebras to like up here, then it would be sort of easier to see this connection, I think. Okay, yeah. That's a very interesting question.
Let's thank Lizzie again.